Alright, so horizontal integration explained using logical intuition. I kind of came up with this example myself, but I'm not too sure. So we'll start with the function, and you could define it as any function. We'll start with y equals square root x, but I guess it doesn't matter. And I guess the difficulty is with the logical constraints of things. You cannot use things like, or you can square both sides, but you would have to make sure that the domain restrictions are, of course, logical and consistent. So if you square both sides, for example, you get y squared equals x, which is the same relationship. But in the first one, there's only one y for every square root x, but in the second one, there can be two y's for square root x. For example, if x equals 4, then y can be negative 2 or 2 in the second example. But when y equals 4 here, or when x equals 4 here, y can only equal 2. Because the square root operator only takes the positive root. So logically speaking, we would have to define the domain, and I guess that is what is very necessary for this explanation of horizontal integration. So we'll start with y equals square root x, and on the xy plane, everyone is familiar with the y equals square root x. Looks something like this, because as the bigger the number gets, the root gets a little bit smaller, just because the inverse function squares, or the inverse function gets steeper and steeper. I guess that's the logic behind it. Or you can think of it as a derivative, which is x to the power, or 3x to the power of 1.5 divided by 2, which is 1.5x to the 1.5. Wait, 1.5x to the 1.5. Oh, no, sorry, the derivative of it would be x to the negative 1.5, x to the negative 0.5, so 0.5. So it would be 0.5, 1 divided by square root x, which gets smaller as x gets bigger. So that means the rate of change becomes increasingly flatter as you go on, if you take limits and whatnot. So this is what y equals square root x looks like. Well, what's the relationship between y squared equals x? So it's the exact same thing. And now let's switch the axes. So in here it's x and y, and here it's x and y, which is a little bit unorthodox because in the Cartesian coordinate plane, you'll typically see the x and y be arranged in the vertical and horizontal configuration like so. But here we're going to swap it around. And logically speaking, this is just a function x of y, which equals y squared, which means it's much the same as y equals x squared, so we can draw it like this. It's important to note that you cannot do this because, again, we restrict the domain as x greater than 0. If x was less than 0, technically it could go here, right? Yeah, I guess why not? Oh, no, because we defined x greater than 0, and as a result, y also has to be greater than 0, because in the original relationship, you cannot get a negative number out of a square root. So this is what it looks like. So when you're integrating a function with relation to, or with respect to the y-axis, you get dy y squared, dy y squared, right? Because x is the function here. This is the important relationship. And as you integrate this, we're going to use an indefinite or definite. I guess we'll use indefinite. That's fine. We'll do y cubed over 3 plus c. So that's what you'll get. And if you plug in the upper bounds, which we'll say is b minus a, we get this relationship. And I guess I guess I could shade it below this, but I would probably like to use Riemann sums, or not Riemann sums, but I guess rectangles to kind of show, which is Riemann sums, but to kind of show how it looks like here. So if you're doing b to a, this is what it looks like. Well, notice that if you orient this into the way this is, you're switching the axes to here, which is the inverse function. And you notice here that it is underneath the, this is underneath the steep curve, which is going to be logically into, which is going to be the same thing as this if you oriented it this way, and a is at the bottom and b is at the top. So much like horizontal integration, or much like vertical integration, horizontal integration finds you, let's say that there's a paraboloid here, and this is a function of x. We'll find you this area, if this is the y and this is the x, because you're just switching the axes. This becomes x and this becomes y logically when you solve x as a function of y. And if you're solving for a function, just a regular integral, then you'll find the area underneath the curve like this. So in this y configuration, you're finding the area between the curve and the y-axis, and here you're finding the area between the curve and the x-axis. Now it's important to note that it's upper minus lower, which did get me a little bit. It's upper bound minus lower, so b is the upper bound, and a is the lower bound. Much like here, b is the right bound, so the biggest number all the way to the right, and a is the left bound. Now it did take me a little bit getting used to, because I would think that integrating with respect to y, or with respect to x, would essentially give, one second. that you would have to take the lower curve because the lower curve would be right here. But no, with the geometric interpretation and configuration, B or the rightmost bound is actually the upper bound, which is a little bit hard to grasp. But that's because it switches like this, so then the right bound is this way. So you're technically flipping this 180 degrees or 180. Let me think. Well, you're flipping it 270. Well, you're flipping it across the relationship y equals x, which is what an inverse function does. And then you're doing that. So it's a little bit hard to grasp. But the integration is simply just going to be upper, lower, x of y, dy, where y is the variable. So yeah, that's pretty simple. And lastly, I think the logical idea is that there is no really logical interpretation. I think there is in thermodynamics. But in traditional math, I guess, and physics, there is no real interpretation of horizontal integration. So like as we know, if we integrate a velocity curve, you get displacement, or I guess meters. Well, I guess the integral velocity equals displacement, m displacement. But the logic is a little bit harder to grasp intuitively when it's horizontal. I still haven't really figured it out, but I guess this would be how much you're losing out on if there is an upper bound. Or that's how much, well, let me think of it now. So if this is the maximum velocity you travel, I guess if that's the maximum speed you can travel, this is the maximum area or the maximum displacement you can travel. So this is essentially all the displacement you are missing out on if your car is not going on a full speed, I guess, which is probably the only logical interpretation of that from what I just figured out. But maybe there are some more practical explanations. But let's say that your car is traveling or can travel at 70 miles per hour and you have a paraboloid like this, or it's not a paraboloid, a parabola here. And 70 miles per hour means that this is your max. Let's say that this is 70. That means you can, and let's say you travel that for 2 hours. That technically means you can travel 140 miles. But if you're like speeding up, then the area, which is the from between the curve and the y-axis, is this, which is technically how much you missed out on. So whatever that is will tell you how much you could have went if you traveled 70 miles per hour for that entire time. I guess that's what I just came up with. But the logic behind horizontal integration, I guess, is more of a geometric explanation rather than an algebraic one or a calculus or physics idea, because it's really abstract. It doesn't really tell us that much. So here we go.